start the last part of this natural deduction. I hope I can finish this part, at least the part that you can do all the homework problems. So last time we looked at a bunch of the rules, and here are some strategies that I used, which I actually didn't write as a table, but you may have guessed this is the strategy that we used. So one way to prove it is you look at the goals, and the goal is a formula, right? And look at the structure of the formula. If the formula has the form of F implies G, then what you can try is assume F, which means that introducing the box with F in the F in the first line, and try to derive G. That's exactly what I just showed you in the previous page for this homework problem. Okay? So basically what it means, let me just write here. So I want to prove F derives G. In order to do that, I can try to establish this part. Okay, so now goal is trying to prove this box, or to find this box. And the second one is, if your goal, somehow you have to find that F and G should be true. So one strategy that you can use is try to prove F and try to prove G, and then use conjunction introduction for these two lines, and we are done. Okay. Now for the disjunction, you try to prove F, okay, and then you can just use or introduction, which will give F or G. Sometimes you may be able to prove G instead of F. That is also equally fine. Okay. And there are some other cases. Cases when you have to prove the final form, which has the negation. And this is actually what we are going to study today. Okay, so I will actually introduce you later, but just for the completeness of the table, I'll just put that. Okay? Okay, we'll come back to this table later. So we look at the most difficult rules about in the natural deduction, which is about the disjunction rule. And since it's not that easy to do, I asked the TA to also go over some problems in natural deduction using the disjunction rule. So let's actually try one more example. So we did this last time, and let's look at how to prove this one. So let's remind us what is the proof strategy to use. So whenever you're given this formula, you have premise, right? So it's always safe to start with the premise. Okay, that is good. Now your last line here should be the goal, the final goal that you want to prove. Good. Then, now let's look at the middle. How do we fill the gap? So what should we do? It's not so obvious, right? Look at the goal. The goal has implication, right? So which rule should we use just before the last line? Or to derive the last line, what should we, which rule that we have to apply? Implication introduction rule, yes. So what that means is you need a box, okay? And inside the box, you will, what is the first line of this box? Are we too fast? Let me repeat what we had. So our goal is F implies G. So in order to do that, this is the trick that we can do. So I'm just using the first strategy here, right? So what is the first line of this box? P or Q, good. Okay, what is the last line of this box? P or R. P or R, right? So if we can establish the box, then we can derive P or Q implies P or R. Are we together? It's no brainer. It's just too simple. Okay, you cannot miss this step. Now the difficult part here is how do we go from line 1 and 2 to n minus 1? This is the challenging part. Okay. Okay, so here, let me just jump ahead and I will give you the structure. Okay, so I'm going to use the line 2 as my case statement. So there are two cases, P is true versus Q is true. I'm actually using phi or psi. So my phi is P and psi is Q. Okay, then I need two boxes, right? So now can you tell me what should be filled in each of the boxes? What I want to do, and maybe let me just say, what I want to do is to use or elimination, which is shown on the left-hand side, right? So I want to use phi or psi, and from phi, if I can derive psi, and from psi I can derive psi, then we are done with the proof to derive psi. Okay? So we just need to fill out the box. What is the first line of the first box? P. Okay. What is the first line of the second box? Q. What is the last line of the first box? Do the pattern match? Okay, very clear. So phi is P and psi is Q. Okay, and what is this psi? Well, let's say just X. Huh? That's not R. It's not R. P or R? Yes. P or R. P or R. Because if I can prove, so here this is phi and this is psi. Okay, from phi I derive X, and from psi I derive X. And what is this X? That's the P or R. Now, case 1, if P is true, I can derive this P or R. Case 2, if Q is true, I can derive P or R. Then, no matter what case that we are in, we can always derive P or R. That's what this or elimination is about. Okay? Why this must be P or R? Because our goal is to prove P or R, which is here, right? So I have to end each of the box with the same formula. Okay? So let me say this again. So I want to prove this fact, P or R is true. There are two cases to consider. When P is true, I can derive P or R. And if Q is true, I can also derive P or R. Then regardless of which case that we are in, I can always derive P or R. Okay? Note here that we use different P or R, P or R, P or R here. But each of them has different assumptions. For this P or R, it is inside this box, right? So you can use assumption about P in order to derive P or R. When you are proving this, you have assumption about Q, but you don't have access to P. Note here that the scope of the box is very essential. When you try to derive this P or R, you can use assumption Q. You can also use assumption P or Q. You can also use Q or implies R as the premise, but you cannot use P. Or anything here in the box cannot be used in this box. Same way, you might say, well, I have P or R, why don't we copy P or R from here to here? This is not also going to work because this P or R is only true when you assume Q is true. Okay? So when you write the rule, okay, when you write the formula, you cannot refer to the box inner than the current box. That's the rule that we say before. Okay? So this is also a common mistake that I often observe. All right. So what we didn't do so far is this middle. Okay? I used the template only. I didn't think anything. There is not much to think. Okay? I just plug in the pattern. That's what I did. Okay? So now we have to fill the gap again. And this time the gap is smaller than before. So that's actually this proof works. You start with filling the gap between 1 and n, but using this deduction rule in the backward way, it becomes much smaller test to prove. Okay? So for instance, the first box, you assume P, and your goal is now to derive P or R. What can you do? Or introduction. Yeah, that's very simple. It's just one line. So there is actually no dot 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 there. So this is assumption. This is also assumption. And P or R is or introduction from line 3. That's it. Okay? Now let's close the gap in the second box. Okay? So here's a bit tricky. I have Q, but I have to prove Q or R. Okay? So what can we do?
You can get R with implication elimination.
With line 1. Yes, we have to use line 1 and line 5 together. So what do we get if we have line 1 and 5 together? Line 5 says Q, line 1 says Q implies R. Using this implication elimination rule, what do you get? You get R. So 6, you get R. Now once you get R, then you can get P or R, right? Which rule? Okay, or introduction. So let me write it here. This Q was assumption, and R is obtained from implication elimination from line 5 and 1, and this is our introduction to line 6. Okay, are we together? So we filled all the gaps in the box. Now it's interesting that when you prove R, we use the assumption in the box as well as the formula that is outside the current box. That is okay. Outside the box is okay. All right? So now I can see what box or how many lines are in each of the boxes. So I use OR elimination to get line 8. Okay? And that is from line 2 and box 3, 4, and then box 5, 7. So OR elimination requires 3 facts to be established. One is the case split, which was P or Q. Another is when you assume P, then I derive Q or R. That's the first part. The second one is when I assume Q, then can I derive Q or R. So no matter which case that we are in, P or Q, we can derive P or R. Okay? So that's why P or R is outside the inner boxes. Okay? Yes?
So the 2 blue boxes, they would be considered like I can't use from each box, right?
Right. So each box is separate. You cannot refer to the other box. Yes.
That's how you don't use line 3.
Question? Yes.
That's why you don't use line 3 for like line 7. You just said 6.
Yes. I can. Yeah, that's a good point. I cannot use line 3, okay, to derive line 7, okay, because it's in the different box. Okay. Okay. Good. So this is the this is a proof. Okay. Now, why I'm saying that this is difficult? I should not discourage you to use OR elimination rule, but often I find that the use of disjunction rule requires some creativity. The other rule, implication introduction, that's actually no-brainer. You have to use it. There's no other choice. Okay, conjunction introduction, you have to do that. Disjunction is a bit problem. Disjunction elimination requires you to have 3 facts, but which are the 2 cases that you have to consider? That is a bit tricky. Okay, that's not easy. Okay.
So for line 9, we would do the implication introduction 2 through 8.
Yes, right. I should also write my justification, which is as you say. Okay, and of course in the homework you also have to write all this justification. Okay. All right. Good point. This one is about associativity of the disjunction. So when you have P or Q or R, you can group P or Q first and then or R. Or you can group Q or R first and then P or R. Now this is actually very natural, right? And you can construct proof in different ways. However, in this class, or at least this page is concerned, I want you to use the natural deduction. Okay? And this is actually not that simple, so I asked the TA to go over this in the dissertation section. Let me try another one, which is about distribution property. So here you have P and Q or R. Can derive P and Q or P and R. It's like multiplication distributed over addition in arithmetic, right? So that's what we can do. Okay. By the way, I don't mind that these problems are also in the homework problem. Okay, as long as you understand and you can write the whole solution by yourself. Okay, so let's see how we can do this guy. Okay, so what should be my line 1? Premise. Okay, what should be my last line? Conclusion. Okay, good. Now, how do we go here? So you have to prove or here, right? Okay. Now I introduced the rule for or, but unfortunately that rule does not apply here. Okay, I'm not going over why, but that's what you can figure it out later. So what I'm going to do is I use or elimination rule. Okay. So since or elimination rule is a bit tricky, let me copy the rules here. So the rule is, in order to derive this, okay. So I need to derive some formula x, but there are two ways to go. Assuming there are two cases, phi or psi. When I assume phi, I can derive this x. If I assume psi, I can also derive x. Then I can derive x no matter which case that we are in. Okay, so that's the rule that we are going to use. Okay, so what we can do is try to get as many formulas from the premise. So in fact, this is a conjunction, right? So we can break this conjunction into two parts. One is P, another is Q or R. So this is conjunction elimination from line 1 in both cases. This is premise. Okay. Now what I'm going to do is, I know P must be true, and I know Q or R must be true. Now the goal here is to prove P and Q is true, or P or R is true. So let's think about it. We know P must be true, that's for sure, but we don't know Q or R is true. But let's assume Q is true. Okay? So informally, if I know P is true and I know Q is true, what can I derive? P and Q. And P and Q is the first of this disjunctive formula, right? Case 2, R is true. I also know P is true. What can I derive from these two facts? P and R, right? So I can derive P and R. That's my proof strategy. Okay? I cannot be sure which one is true between Q or R, but if I assume Q, I can derive P and R is true, from which I can derive the conclusion. If I assume R is true, then I can derive P and R is true, so from which we can derive also the last line. That's my proof strategy. And that gives enough idea about what case split to use for the disjunction elimination rule. So let me write this way. This is my case split. I will split the case into two. Case 1, when Q is true. Case 2, when R is true. Which means that I need two boxes for each of the case. So one box is when I assume Q is true. Another box is when I assume R is true. Okay? Now, in each of these assumptions, what should I derive? What is my conclusion? In each of the case, when Q is true, what is my goal to prove in the box? It's actually this guy, because this is my X. I need X. So I will write this guy. And I realize my box is too small. That's okay. This is my template. If I use case split or Q and R to derive the conclusion, this is the thing. There is no other formula that I can write here. There's no other guessing. Okay, this is the one that I have to do. Okay, now then our task is to fill the gap. Okay. Okay, so this is my line 4. So from 1, 2, 3, 4, how can we derive this line P and Q or P and R? Yes. Yeah, look at line 2 and 4. That's a very good plan. We know P is true from line 2, Q is true for line 4, so I can say P and Q is true because this is an introduction for line 2 and 4. By the way, this is assumption. This is assumption. Okay? Now I don't have space between line 5 and the next line, but I don't need it. Why? How can I go from line 5 to line 6? Or introduction, because P and Q is one of the disjunctive term, and whatever, no matter whatever that I make a disjunction with, that's a still valid formula to derive. So that's or introduction from line 5. We are done here. Okay. The next box is also dual because the reasoning is symmetric. Okay, let's actually go over that. So line 7 we assumed R. Line 8 we can derive P and R. Ooh. No problem. So from line 8 we can derive P and R from line 2 introduction to line 2 and 7. And line 9 is or introduction from line 8. And the last line, since we filled all the gaps, this is or elimination from line 3, 4 to 6, 7 to 9. So n is actually 10. Okay, so let's go over this proof together. Okay, so we start with the premise P and Q or R. I can get P and Q or R from these premises by breaking this conjunction. Now when I assume Q, I can also derive P and Q because I already know P is true, and I will also assume Q is true. And from P and Q, I derive P and Q or something else. Now, the second case is I assume R. The same way, I can derive P and R. And P and R with any other disjunction is also possible. So that's why we get this. And what we established so far is, regardless of the assumption Q or R, we can derive the same formula line 6, line 9. They are the same formula, which means that this formula can be outside the box. That's what it says here. If you can derive x from phi, you can also derive x from psi. This x can be outside the box. So that's what we did. Yes?
Why is that 3 also in the last line? Or, yeah, 3, 4, 6, 7,
3, so you need 3 fact to establish. This is 3. This is box 4 to 6. This is box to 7 to 9. Okay? We need 3 things. One is case split, another is case 1 box, another is the other is case 2 box. Okay? Yes?
For line 6,
Uh-huh.
why don't you also say from line 3 and 5? Why you just have 5? Same thing for 9.
I'm sorry, what? Line 6, what is your suggestion?
You just have a thing from line 5. Why can't you put for line 3 and 2?
Line 3 has nothing to do with line 6. Am I right? And showing other formula than 6 does not help us to derive the last formula. Okay? So you can try to use line 3 and line 6, but then I don't see how you can prove the final formula. Because final formula should be exactly the same as line 6. Okay? All right. So we are done with the most difficult proof in the natural deduction. Okay. So after this comes easy. This is actually more intuitive, or maybe easier to understand. Okay. Although you'll also see there's something coming out from these things later. Anyway, let me not spoil that for now. So what we didn't do is the negation rules, right? So the last rule of the proof structure that I skipped, that's what is shown here. So there are two rules of, I'm sorry. Okay, there are two rules about negation here. So one is negation introduction and another is negation elimination. Okay, and also there is something close to these guys. It's called bottom elimination. Okay, so far we haven't seen bottom in the use, right? But these rules are necessary. So bottom is like false. Okay, you can just assume that it's false. What this implication introduction rule is saying is, suppose you assume phi, and somehow you lead into a contradiction, which is denoted by this bottom. Okay? So if all the other steps are correct, then which line should be blamed for? Here's the thing. Your assumption, you start with some assumption. We don't know whether this assumption is true or false. But after that assumption, I use all the valid rules. And then somehow you got the contradiction. Then the formula, the line that has to that need blame is actually the assumption. Because your assumption was wrong, that's why no matter what you do, you get the contradiction. So what implication, what this negation introduction rule is saying is, if you assume phi temporarily and then derive contradiction, then you can conclude that negation of that assumption is actually true. Your assumption was wrong. That means your negation of that assumption must be true. That's what negation introduction rule is saying. Are we together? Okay, good. Yeah.
So basically, if you assume that something is false, right, and then and the answer is again is wrong, then you can assume that.
You have to switch the assumption. Yeah. We don't know whether this is false or not when you assume. But if you find out later it is a contradiction, then your assumption has to be negated.
What's an example of finding out that it's false? Like if you just can't
we'll come across the example later. Okay. Let me just introduce the other rules. So the dual is about so this is introduction of the negation. So negation was not there before, but now it's being introduced. Dual rule is negation elimination rule. And so here, this also, you can imagine. So there's a phi that you establish. And at some other point, you also establish negation of phi. But these two cannot be both true at the same time. That leads to the contradiction. So from these two facts, these two contradictory facts, you derive the contradiction, which is denoted by this bottom symbol. Okay? So this is the negation elimination rule, because this negation is gone when you apply this rule. Now, this is actually a bit unintuitive at first sight, which is about bottom elimination rule. Okay? This rule is saying that if you somehow derive bottom, then you can derive any formula. Okay? If you got a contradiction, then you can derive any formula. Okay? So I'll get back to this point later, but let's try to do some exercise. The first exercise is actually shown here. So imagine that we have two formulas. P implies Q, and P implies not Q. This derives not P. Okay, what does that mean? So let's think about it. If somebody says if P is true, then Q must be true, and also you're also given the fact that if P is true, then not Q is true. Okay, does these two statements contradictory to each other? Huh? No, it's not. I told you that if P is true doesn't mean that P is true. If P implies if P, then Q is true. Doesn't say anything about whether P is true or Q is true, unless you establish the P part. Okay. So these two formulas itself do not contradict each other yet. But if you assume at the same time P is also true, then it starts to create a problem. Why? P is true. So from P is true and P implies Q, what can I derive? Q. And also from P and P implies not Q, what can we derive? Not Q. So I can derive Q and not Q together, that's a contradiction. But if you don't have P, that is okay. They do not contradict. So what that means is P must be false in order to make consistent assumption here. Right? That's the goal. That's the proof idea. So let me actually prove this in natural deduction. So in line 1 and line 2 is actually clear what to write. Okay? And line n, I don't know, but it's, let's say we have this. Now let's apply our strategy. So I want to prove negation of P. Which rule should I apply to derive the last line? You have three choices, A, B, C. Should I do Socrative or just do this? It's A, right? The negation introduction rule. Which means that what do I need in the box? I need a box. Okay? So negation introduction rule is saying that if you want to derive not phi, then assume phi and try to derive contradiction. So in the box here, my goal is to derive not P. What should I assume? P. And what should I try to derive? Bottom. That's what it is here. Okay, I have to derive bottom. Okay, ultimate goal is to derive bottom. Of course, we need a Q and not Q. So that's this part. So this is premise, assumption. Okay, so how do we close the gap here? This is what we just spoke about. Yes, from which two lines should we look at? 1 and 3. Okay, implication, elimination for 1 and 3. What do we get? Q. Okay, now another one, implication 2 and 3. What do we get? Not Q. Okay, I got Q and not Q. Which rule allows me to derive bottom? C, the negation and elimination rule. Okay, that is the last one. I got phi as Q, so you have Q and not Q, we can derive bottom. So that's this. Okay, the proof is done. So let's read together. And this reading is exactly what I said in the beginning. So let's assume P implies Q is true, and let's also assume P implies not Q is true. Now let's assume temporarily P is true, then I can derive Q and not Q. And since Q and not Q cannot be both true, we get the contradiction. What to be blamed for? That's P. So P has to be negated. So we get the not P. Done. Okay? So that's the last one is negation introduction for line 3, box 3 to 6. Okay? Are we together? Okay, good. So then, let's go to the next one. Okay, so you know what? Let me skip this guy and I'll ask the no, actually, let's do this. Okay, this is actually a very useful fact that not P or Q can derive P implies Q. Okay. Okay. So line 1, we have not P or Q, and line N, we have P implies Q. Okay. So I will give you a hint. So here I will use or elimination to derive the last line. And my case split is not P and Q. So which two boxes do we need?
You just make two boxes, one with not P and one with
Yes.
Q.
I need a box that has not P in the first. Maybe I should. I need another box that has Q. And what should I have in the last line of each box? P implies Q. Good. Okay, so that part is clear. So now let's try to fill each of the boxes. Okay. All right. So in the first box, we assume not P. Okay. How can we derive P implies Q?
You're gonna have another box inside the box with P.
So we have to derive P implies Q, right? So what is the rule that we can use to derive P implies Q? That's implication introduction rule, right? So in the box, what is my first line? P. What is the last line? Q. Okay, so let's try to close the gap. How do we go from line 1 to 3 to Q? Look at what you have. You have not P or Q, you have not P, and you have P. What can you derive?
You can use that negation, elimination.
Yes, what can we derive here?
The
The bottom, okay? So I know not P is true from line 2. Line 3 says P is true, so I can derive box.
what's it
Okay.
called?
Bottom. Bottom. For now, okay? So, okay, we derive bottom, and how do we go from line 4 to the next line? Bottom elimination. From the bottom, you can derive any formula. This is a magic rule. Okay, so you can just derive Q. And since you prove by assuming P derive Q, you have P implies Q, that's done. So the first box is proven. The second box, you have Q. Okay, now you have to go to P implies Q. Okay, you cannot use the box, the formulas in the box 2 to 6. Okay, let me just finish up this and let me put the question here. So, how do we get to P implies Q? Again, look at P implies Q. Which rule do you need? Implication introduction. So that is P and Q. So from this, you can derive P implies Q. Okay, so line 8 is assumption. And we have to fill this gap. But actually, there is no gap here. Right? We can derive line 9 directly. What rule justifies this? Copy rule, because line 7 is already there, copy 7. So then this is line 10. We can get P implies Q from implication introduction to line 8 and 9. And 11, we get P implies Q by disjunction or elimination, line 1, 2 to 6, and 7 to 10. Okay? Are we together? Yes.
Since what you're trying to derive is P implies Q, wouldn't it be easier to just assume P and then derive Q because not P or Q. If P is true, then Q has to be.
Well, you have to have P in the antecedent. So
Yeah.
how can you do that?
Well, you assume P, and then you derive Q, because then it would be false or Q, which is just Q.
So what are the suggestions here? I'm not clear about that.
At the very beginning, at like line 2, you assume P. And then you
Line
use that.
2, you assume P.
Yeah. And
Okay,
then
why don't you
use-
write your solution and post on the
Okay.
piano? Let's actually talk here, because it's actually difficult to modify here. But that's exactly why we want to do further discussion. Okay. By the way, there can be actually more than one proof here, and sometimes some proof can be simpler than the other. So it's possible that your proof can be simpler than this. Or if it is, unless it is correct, okay?
Logically, why does the bottom elimination rule work at all? I mean, I'm a little confused as to why you can go from a contradiction to assuming it.
Okay, I think you're suggesting some different way to prove, which is okay to try.
No, I'm just wondering why it works. Why, if you get a
Why
contradiction
do disjunction and elimination work here?
or anywhere logically, like why does that rule exist?
He's asking about bottom elimination.
Are you asking about bottom elimination? Are you?
Yeah,
agreeing
bottom
with that?
elimination.
Bottom elimination. Well, from why it works?
Yeah.
That's the rule. Okay.
Like, can you give me like a straightforward example of that?
Yes. So something that is actually rules 1 data is soundness and completeness theorem. So each of the rules has certain meaning there. So let me just jump ahead, since there was a question here. Each of this one can be written as a formula of this. So if this one can be written as this. And if you look at this formula, okay, so I turn this arrow into the implication. So bottom implies phi is called the tautology. And that tautology means that the formula is always true, no matter what cases that you are in. Same for phi and not phi implies bottom is also tautology. So this is always a true formula. Okay? Now, the rule is actually necessary because if you omit this, there are some formulas that you cannot prove to be true. Okay? Now, in terms of the informal sense, what this rule is saying that if you make a contradiction, then anything can follow from your assumption. Now, note here that in the beginning we said if you believe this is true, then you can derive these formulas, right? Now, if you have nothing to believe, then you can derive any formula. That is it. Okay? So this is not probably very intuitive at this point, but maybe when you touch on the semantics of propositional logic, it will start making some sense there. Now, actually, we are done with natural deduction rules. And at this point, a valid question like this is, why this is a correct set of rules? Can we not design some different set? Yes, it is possible, and there are many different versions of natural deduction. Okay? And that distinction comes from which are so-called primitive rules and which are derived rules. Okay? So some textbooks has this set of rules as a primitive, and there are also other rules that you can derive from the primitive rules, while in some other textbooks choose different set of primitive rules and then derive other things. Okay? So depending on which version that you look at, your set of rules given for the natural deduction may look different. However, in this class, we are not going to worry too much about the differences between derived rules and the primitive rules. In fact, the next set of slides is about the derived rules. Okay? But before that, the question?
So in line 2, you assume not P is true.
Right.
In line 3, you assume P is true.
Right.
And that creates the contradiction, so
Right.
the bottom.
Right.
So how do you get Q from that?
Because the bottom elimination rule says if you derive bottom, you can derive any formula in the next line. Any. Phi is any formula.
Couldn't you just
Any.
do P implies Q?
Yeah, you can do.
Would that solve the...
No, it doesn't solve.
Oh, how come that doesn't work?
If you stuck in a box, if you stuck in that scope.
So the question, maybe, I'm not going into that now because I have to go to the other slides. So he is suggesting, why not we simply use P implies Q here? Okay? And the problem is, somebody already said, you can still P implies Q stuck inside the box. You don't get it outside. You need it outside. Let me actually go through, and if you still have questions, let's talk offline. Okay, so I'm done with the primitive rules, and this is a set of rules that you see from the textbook. Now, something that I didn't say, actually all of the rules are kind of paired, but actually there is no introduction for the bottom. Okay, and previously I also said if you have phi, you can introduce double negation. In fact, this is not a primitive rule, although this is a valid rule to use. This is actually the derived rules, and we are going to see why it's derived rules. Okay, but all the other rules are already there. Okay, and let's go to see the other rules. Something that is useful here is modus tollens, which is to say that phi implies psi is true. If you know that this is true, and if you also know that negation of psi is true, then you can derive negation of phi is true. This is modus tollens. So for instance, if I know that n is divisible by 4, then I know n is even number, right? But this itself doesn't say whether n is divisible by 4 or doesn't say n is even number, right? Don't get confused. If you have a statement like this, this itself doesn't say whether n is divisible by 4 or n is even number. It doesn't say that. Okay? Now, we are given additional information now, which is n is not even. Okay? So from these two, what can you derive? N is not divisible by 4. That's what you can derive. So this is modus tollens. Phi implies psi is true, but you also know that not psi is true, then not phi is true. Okay? That's what the modus tollens rule tells you. Okay, so and this rule is actually very useful, but it can be actually derived from the rules that you already know. So you already know the whole set of rules that you can use for the homework, but some rules like this will help you to write the proof shorter. Okay, so let's see what that means. So suppose I don't have this set of rules, okay, but I can use the other rules that you've learned so far to derive the same conclusion. So I know phi implies psi is true. I also know negation of psi is true. But I don't know this modus tollens rule, and I just try to derive negation of phi here. Okay? So without using the modus tollens, how can you prove this? How can you go from lines 1 and 2 to line n? Any idea? So these are the premises. These are the premises. Okay? Negation introduction. Yes, that's the rule that we can use, because my formula has the negation front. So what I can do is I assume phi and try to derive the negation. If I succeed, I can derive last line. So this is the negation introduction from line 3 to n-1. And this is assumption. Now, how can we derive from line 1 to 3 to bottom? We did similar thing before. So I know line 3 is true. I also know line 1 is true. What can we derive? Psi. Okay? This is implication elimination for line 3 and 1. And then I can derive bottom because line 2 and 4 are contradictory. Okay? So this is negation elimination for line 2 and 4. Okay, so we are done. So we can prove this fact without using the modus tollens, but sometimes it's good to remember this pattern because that will help you to solve a problem like this. So we talked about this problem before. We talk about this. If this is phi, then this is psi. if phi has a vowel on one side, it must have an even number on the other side. Okay? And one of the unintuitive thing is actually you have to flip 7, because 7 tells you that this is negation of psi. Okay? So you can actually get the negation of phi. Okay? So in other words, this rule, phi implies psi, is actually equivalent to say this one. Okay? So that if you don't have an even number on the other side, then the other side must not have a vowel. Okay? So that's the kind of application of modus tollens. The other rule, which we didn't eliminate as in the set of primitive rules, but this is actually not primitive. It can be derived from the other rules. Okay, so suppose we don't have this rule, but can we actually derive this double negation from the rules that we have now? So that means can we derive double negation of phi from phi? How can we do that? Negation introduction rule. Good. Because this one has negation of some formula. So I can use the box. If I assume negation of phi and I can derive bottom, that allows me to derive negation of that negation of phi. Okay? Right, so this is my assumption. This is premise. And line 3 is actually immediate. Okay? This is negation elimination from line 1 and 2. 1 and 2 are contradictory to each other. So we get this. And line 4 here, you can introduce the negation. So line 2, 2, 3. That's it. So again, you can derive not phi from phi without using this double negation introduction rule. So in that sense, double negation introduction rule is kind of macro. Okay, you don't have to rely on it, but if you have a macro, sometimes your program becomes simpler. The other rule is called proof by contradiction, and this is working like this. We have seen similar rule like this before. The idea is you start with the negation of phi and you somehow prove contradiction. Then you can derive phi. Okay? Right? So this is actually similar to the rules that you saw before. If you have phi and derive bottom, what can you conclude? This is a negation introduction rule, right? But now what we have is a slightly different thing. But so if you assume not phi, so let's say this way. Proof phi contradiction works like this. You have to prove phi is true. Okay? But in order to prove this, you're assuming that negation of phi is true. And from this, if you can derive contradiction, then it follows that phi is true. Okay? So let's do this. Suppose we don't know this rule. So our goal is, suppose we can derive this part. Okay? From this, we can immediately get what? From these things, without using the PDC rule, what can you derive? You assume negation of phi and you derive contradiction, right? Not phi. So negation introduction rule. Okay, so that is not phi. But we know that double negation elimination rule can be applied. Okay, so you can get phi. So you just need one more step here. Yes?
What's the difference between deriving a rule and proving a rule?
Okay, so derived rules can be derived from the primitive set of rules, not vice versa. Okay?
Do the primitive rules have to be proved first?
I said before that depending on what you set as the primitive rules, some rules that you classify as primitive can be derived from that set. So different logicians have different different set of primitive rules. Okay, but we are not going to worry too much about it. For this class is concerned, we already established primitive set of rules, and I use these rules to derive the new rules. In fact, how many inference rules are possible in natural deduction? Infinitely many. You can do that. So you can derive infinitely many derived rules here. Okay, I'm not going to show all of them, of course. So I'm showing only the useful derived rules that you can use for your proof, and they have all the good names here. Now, one of the rules is called law of excluded middle, and this is another interesting rule. It doesn't need any premise. You can just write the formula phi or not phi. Again, this is a magic rule. Okay. In any line of the proof, you can always write this rule. You don't need to refer to the formulas that you established. You don't need it. Okay, you just need to write phi or not phi. Now, some of the problems that you are going to do in the homework will be useful to use this derived law of excluded middle. Okay. But also this rule is very difficult to use because you have no clue what to use as phi. So let's look at an example. So here we have seen similar derivation before, which was actually from not P or Q, we derived P implies Q. But opposite direction of derivation is also possible. So here we want to derive not P or Q from P implies Q. Okay? So this is the magic rule that I'm going to use. Suddenly, I will say not P or P with no reason. I don't tell you why I use that. Okay? This is what mathematicians does. They write the proof in some ways, assuming that you guys are on the same page, but you don't have any clue why these people assume that particular assumption there. What I'm going to do is, since I have a disjunction, I want to use the case split. I can have two cases, not P and P. From not P, I want to derive not P or Q. From P, I also want to derive not P or Q. Okay, are we together here? Okay, except for the line 2, the other thing is actually straightforward application of disjunction elimination rule, right? How do we close the gap in the first box? That's OR introduction from line 3. Good. That's done for the first box. Okay, how do we do for the second box? So I assume P. Okay. I also know line 1 and 2. From these, how can we derive not P or Q?
You derive Q.
You can derive Q because from line 5 and line 1, that allows me to derive Q. So this is implication, elimination from line 5 and 1. Okay, so this is assumption. This is law of excluded middle. This is premise. Line 7, again, I know Q, so I can derive not P or Q, right? Or introduction. So this is my line 8. We are done. So or elimination from line 2, 3 to 4, 5 to 7. Okay, so let me read from the beginning to the end now. So in the beginning I said P implies Q is true. That's the premise. I know not P or P is true. Okay? If I know not P, then I can derive not P or Q easily. Just using or introduction, right? Are we together? If I know P, I can derive not P or Q with some more steps. If I assume P is true, and since I also know P implies Q is true, I can derive Q is true. If I know Q is true, I can derive not P or Q. We are done. That's what each box is saying. Okay? Let me repeat. In the first box, we assume not P is true. From this, easy to derive not P or Q. From the second box, I assume P is true. But since P is true and P implies Q is true, I can derive Q is true. From this, I can derive not P or Q is true. So no matter which case that we are in, not P or P, we derive the same formula, not P or Q and not P or Q. So we can derive not P or Q outside this case statement. Okay? Yes, question?
I'm confused at how you got not P or Q in line 4.
Line 4 is to use or in introduction. So not P is one of the disjunctive sum. So you can make a disjunction with any other formula, including not Q, including Q.
We don't know if Q is true or not, though.
Doesn't matter. Doesn't matter. So or introduction rule was saying that if you know one of them is true, then you can make this. You don't have to know whether psi is true or false. Doesn't matter.
So not P is true.
Not P is assumed to be true in the box. Okay, so in the box you can say not P or something. That is fine. Okay, question?
What's L again?
Law of excluded middle, the one that we just saw in the previous slide.
So, and then we're just saying it's true.
No, that's the rule. That's the rule you can use. Okay. Now this rule can be also derived from the primitive set of rules, but we are out of time, so I'm going to ask the TA to go over these two. Okay. But most of them are actually pretty similar. Question? For the test, you have to memorize all the rules. I'm not going to give you the rules.
You have to remember whether a given rule is primitive or not.
No, you don't have to. Okay. So these are the derived rules that you saw just now, and this is the complete set. Okay. So in main proof, you see that we assume some formula F and derive G, and also assume G and derive F, right? So if you can prove these things, so actually this is one of the examples. We actually showed this proof. So assuming the left formula, we derive right formula, and assuming the other right formula, we derive the left formula. So in that case, we can say that these two formulas are provably equivalent. Okay? So they are actually just the same, they have the same meaning. Okay? So we are going to write this one to mean that this is true. Okay? Now something that I want to emphasize, and here there will be some tricky things that we'll explain next time. There's some disagreement between classical additions and intuitionistic additions regarding what are the provable what formulas are provably equivalent. Okay, so some of the rules that you saw, like these rules proved by contradiction, law of excluded middle, and this double negation and elimination rule. Intuitionistic logicians do not approve these as valid deduction rules. Okay, so under the intuitionistic logic, which we're not going to the detail, but there are some merit about that point. The position from them is if you allow this type of the set of rules, then you will have very unintuitive proof. Okay? And okay, that's the proof that we are going to see next time. Okay?